So our colloquium speaker today is Professor Kang Wang from UCLA. Professor Wang is a very distinguished researcher in the area of devices and systems based on these devices. He got his bachelor's at National Chung Kung University in Taiwan, got his master's and PhD at MIT, was a faculty member at MIT, and then moved to General Electric's corporate research lab. After staying there for 6-7 years, he moved to UCLA, where he's developed one of the largest device research groups in the country. So Professor Wang is also the inventor of a strained layer MOSFET. He's inventor of a quantum SRAM memory cell. He's also inventor of the band-aligned superlattice device. So in addition to a number of technical accomplishments, he's also played a large leadership role in the device community. So he's very well known to be the director of two of the largest institutes in the nanoelectronics area. So he was the researcher of an institute called FINA, which dealt with using nanoelectronic devices for new architectures. This was a SRC and Department of Defense funded effort. He was also the director of the Western Institute of Nanoelectronics, which was funded by a number of entities, including the state of California. So it's my pleasure to welcome Professor Wang to University of Washington to deliver this colloquium.
Thank you very much, Professor Anatram. And he almost gave half of my talk already. So it is indeed a great pleasure to be here to see many of my friends and Professor Huang's invitation and many of my Professor Lee and others to be here. So I wanted today to share with you my thought about what would be the next few generations of electronics in general. So I adapt the name, as you can see, energy scaling of Spintronics. The most critical challenge of today's electronics is energy dissipation. So I would want to share with you, and we can discuss after that, see what do you think the next few generations, which is important in my opinion, for the young generations. So the work is actually, as Anna pointed out, supported by FINA. It's the early generation from 2003 to 2013. And you know, in the US, you want to renew something, you had to change the name, right? So in 10 years, we changed that to FAME. And this is the name FAME. I see the backscatter problem of the panel. So, and that is essence to look fundamentally, how can information system change? And we got to go from fundamental aspect of it, that is the materials aspect and the physics aspect of it. And as you mentioned, the work also in part supported by the California Nanosystem Institute, which provide all the infrastructure for us to perform the research. So, what was the fundamental need to be changed? So earlier in 2003, the semiconductor industry asked me, said, can you do something which will lead to a fundamental change in 2020? And they always like this called the 2020 vision, right? That's the reason 2020 is coming up. So that was the center. But then, as I mentioned, so 2013, we changed the name to, the name is now important, just a name, so that it catch the attention of the funding agencies. So what's most important thing is to look at fundamental, and that is that we're looking for new unconventional materials. Several aspects of it. The key is this is the mission-oriented research. Mission-oriented meaning to help in semiconductor in the future have new generation of electronics, and therefore they continue their business. So we're looking for the new low energy, high performance devices, circuits, and systems. That's what we're looking for. And the kinds of material we are looking for is, for example, multiferroic and multifunctional material, such as a transition metal chalcogenide, in which meaning that you can couple the electrical signal with mechanical, with magnetic, at least 2 parameters is a single phase material, and that's called multifluoric. The multifluoric the name is conceived in 1994 by the gentleman called Hans Schmidt. He created this, the name. And that, what is so fundamental about it is be able to electric field to control magnetic property, or from electrical to control mechanical, and mechanical control magnetic property, etc. That's the purpose. The other area is looking at multi-metals. Now, multi-metal consists of heavy metal, like a tantalum, for example, now in which the so-called spin-orbit interaction, that is when you have spin and you have orbital motion at the same time, they interact very heavily, and that result into called the spin Hall effect, and that's recent discovered that the spin Hall effect is much larger than anticipated before, and very important, as I will show that later. Now, if the spin-orbital interaction come at such a high extent that semiconductor, which you all know that has conduction band on top, valence band on bottom, the spin-orbital interaction has little band in below the valence band. Now, if one pushed spin-orbital interaction higher and higher, such that the valence band meets the conduction band and in essence flip over. So the character of valence band becomes conduction band, and character of conduction band becomes valence band. And there's a topological change in phase in the wave function, the sort of topology of the wave function change in the K-space, momentum space, and that is called topological insulator. So if one push the spin-orbital interaction to such extent, then one has so-called topological insulator, and this is discovered 2008, known as one of the greatest discovery in 10 among 10 in all field of science, and that's important. Now, topological insulator turns out is also a van der Waals material. So now the recent interest of two-dimensional van der Waals material, you can put them together, form the artificial two-dimensional superlattice, and those give you tremendous opportunity in the future. And those are the kind of material that we are looking at. Now, so why are we doing all this? Is to solve the major challenge of the power consumption of information processing. You all know Google, right? You all know Facebook. But of course, you have to know Amazon and Microsoft, who are right next door of yours, right? And you may or may not know, they burn tremendous of power. The servers, look at this server farms over here. This is one of the Google server farm. You look into detail, they actually have all kinds of pipes. Look at beautiful pipes. What they do for? They are doing for cooling. And because this, as I cited New York Times in 2010, this Google data center alone drove 1/4 of gigawatts. That is 1/4 of a nuclear power plant alone. And then every 3 years, it's about double. So it's going to this year, probably half of the power plant just support this. And of course, you need a cooling, even worse. You need cooling. Where do you put a cooler? Your servers are next to your riverbank. And of course, you have a lot of rivers here, but you are running out of river, where do you put them? You put ocean, near the ocean with the seawater cooling. That's what Google is planning to do. So what it says is that the computer servers must be made more energy efficient. What was the problem? Well, it rooted back to the challenge of fundamental device today we use every day in the PC, in the cellular phone, and et cetera. Those will be the MOS transistor, which has a gate and source and drain. And actually, it's ideal devices. We use that since 1965 to now, almost 60 years, 50, 60 years now. It scales very well, meaning you shrink it down, it works better, the density higher, the energy turns out lower per device. But the chip per chip is almost constant. And what is the problem when you get smaller and smaller? It turns out the leakage current from gate to down here, because the oxide is from thin oxide leaks, and that causes this leakage current. There's another problem is a so-called substrate leakage current, is that when you turn on and off. When you off, the devices are not completely off when it's small. When they're large, they're okay. So in order to avoid this leakage current, one use high K. In other words, high dielectric constant of insulator, so I can make this thicker. The tunneling current reduces much better. And of course, industry are very creative to use a strain. I was one also responsible for some of the strain. Introduce your today's PC, make them faster. So you can see that. And all this problem, how do I eliminate this leakage current problem? The best is get rid of voltage. Don't apply the voltage. So all the problem comes from that power has to apply all the time. Right? Without power, you have no leakage current. No voltage, no leakage current. The secondary is the dynamics. As you all know, there's a dynamic energy dissipation, which when the system turn on and off during that exercise and on and off, and that gives you CV squared times F being frequency. Now, since 2005, frequency is no longer increasing. Your PC clock frequency sets about 2 to 3 gigahertz are now increasing. In the past, it continued to increase. Why so? Because before we could reduce voltage as we scale. So we can still keep our frequency higher, maintain the power dissipation to a controllable manner. You can reduce the voltage because you will shrink it down. E field is constant, voltage drops. So V square takes over the frequency. That's good. But now, if it comes to smaller, what happens too? Because you cannot reduce the voltage anymore. Why so? Because every time you turn on a transistor, it's thermally activated. So for a decade of on and off ratio, you have to be on and off. On-off ratio, a factor of 10, you need about natural log of 10 times room temperature, 25 MeV. So that makes it 60 millivolts per decade of change. Normally for transistor, you need about 4 orders magnitudes. That makes it into quarter of volts. So you cannot shrink it down to below quarter of volts anymore. And we are now at about 0.5 volts. You need a headway. So that's problem is called, this is called subthreshold slope. And that subthreshold is another problem. So there are 2 major issues. One is power on all the time, and the other one is subthreshold. You cannot do anything about it. That's the reason that you have power dissipation problem. So that leading to my talk is talk about energy scaling, and you said I already said something already. Now, for today's CMOS, what are people working on? I call them CMOS derivative. CMOS derivative is nothing but use a different kind of structure to reduce subthreshold. In other words, to have better effective control by the gate to reduce the voltage as much as you can and to reduce subthreshold voltage to a lower value as possibly. But what I would like to share with you today is use Spintronics as alternative. And in that, I will take you to what is today's information process system, which is processor memory, and how could I put this magnetic memory into the system is Spintronics, in such that I can reduce energy by both ways, by solving non-volatility, the volatility, which is power on all the time, and by possibly reducing the subthreshold behavior as well. And I will talk about the MeRAM, which is Magnetoelectric RAM versus current-driven. So I'm talking about current-driven memory versus voltage-driven memory. In passing, I should say that we also, we have an NSF Engineering Research Center in which we look at the multi-phoric system, meaning I could use electric field to control magnetic property, not necessarily by current only. It's well known, Ampere's law gives you, when you have current going through, you produce magnetic field. And that's classical way of doing it. But if one can use electric field, then it reduce energy much better. So, and in passing, I should mention about spin Hall, as I mentioned, and topological insulator. And if that can be done, I believe we can have the system power off all the time and can turn on somewhat very quickly without booting. And then, therefore, that may be leading to so-called memory-intensive and neuromorphic system. I recognize the brain is a memory-intensive system, and I'll go through it quickly. So the CMOS I call that the CMOS roadmap. The roadmap started from 10 micron about 1960, and moving to 90 nanometer, which strain, Professor Anna Armstrong pointed out the strain to improve the performance in the 90 nanometer nodes, and that continue to about a few years ago, 22 nanometer, use a FinFET, that means a very thin layer of silicon as a bulk material, which to improve what? Improve the gate control, meaning improving the substrate threshold that I mentioned about. Now, of course, last year, or close to this year, supposed to be 14 nanometer. It's a blank. Why is blank? Because the industry, I work in industry closely for past 20, 30 years. Industry are there to make money, right? For sure. Now, any product coming out in next year, I won't tell you. Should I tell you? I tell you I have lose competition. So that's the reason the blank. Now, 3 years, 5 years down the road, or 10 years, I don't know what I'm going to do. So that's all work together. And that's the reason it gives you all the sort of possibility, right? But whatever I'm going to make money next year, I won't tell you. That's the, so you have to know how to work with industry, and that's exactly the spirit. So that's so all this is nothing but, in my opinion, is to have very good gate control, reduce the substrate threshold voltage. How do they do it? Make it thinner and thinner there, so the control of the gate is more effective in this way. Now, this is divided by the DFT and the Boltzmann transport calculation of different ultra-thin silicon, bulk silicon, meaning that if I reduce the layer of the silicon from 4 to 1 nanometer, for example, and this is 1 nanometer, your substrate threshold, remember I told you 60 is the limit. Now, of course, it goes higher and higher, you could shrink and smaller and smaller. That means the effective control is kind of less in the thin layer. And in the thin short channel case. And this is the thicker one. So you want to be as thin as possible. That's the reason the industry is moving to that direction. What is the ultimate of that? Single atomic layer. What are they? They are 2D material. Today, the people working on it. For example, one example is molybdisulfide, and there are many others. Topological insulator is also a van der Waals single atomic layer material. And look at that. They are actually at the 5 nanometer. They are 60-some nanomoles. In here, they are about 80. So the thinner, the better. That's what it's doing. Of course, prefer if you get all this one down, that would be better than the people working on tunneling FET, which to bring this way down to here. That's the CMOS, I call that CMOS derivatives. Now, I will not talk about this. Today, I will talk about the Spintronics as alternative. Spintronics, generally speaking, they can be classified in 2 areas. One is single spin, electron to spin. Single, you manipulate one by one. Well, to manipulate one by one, normally energy, the energy, stable energy is very low, so you need to go to low temperature. For room temperature, one must use collective spin. And collective spin, the only one at the room temperature that we know today in all physics is magnetism. It's magnetic. And they work at the room temperature. Single spin will never work at room temperature. Our industry friend told me, Kang Wang, we have to work at room temperature because I cannot carry a magnet running around, right? So that's the reason we collective. And the collective spin have another advantage. I'll show you that. Before I do that, I'll take you back why this is so important with collective spin. And I will take you back to the information processing system. Generally speaking, a PC like this, or your tablets, all have CPU and memory. And I can draw architecture as following. Any CPU consists of logic unit, arithmetic logic unit. It has some small amount of memory, which I call cache and register, which meaning to get which is next execution. And after I execute it, this result, I put it somewhere first. That's right. And the red one are normally, this part is based on the CMOS technology known as SRAM, and they are volatile. So volatile and indicate in red. Now, when you buy a PC, people give you 8 gig or 12 gig memory. They are DRAM, dynamic memory. They are also based on MOS technology, so they are volatile. And this puts right here. Now, so what happens, you have loaded Microsoft program, right? Office, you don't stay right here. When you click PowerPoint, it immediately call this program, get this information loaded into DRAM. And then when you execute it, every time you push the button, it goes from here to there, information transfer, right there. When you do a calculation, exactly. So this data bus becomes very busy. And the reason you have to do that because all these are volatile. Only this non-volatile. And this bus is known, the traffic of this bus known for Neumann limits. It's a latency issue, how fast you go, become the computational limit. In the cloud computing coming up, this is even worse. So this is the problem we have. Now, clearly, why don't we change this one to this kind of memory? The reason is you need a very high endurance because your clock frequency is a gigahertz. So one has to go in and out very, very frequently. Most of this memory, including your flash memory, won't last that long. You need a 10 to the 15 writes. Every time you can write more than before they fail. So that's important. Of course, you don't have to be this architecture doesn't have to be CPU, a logic unit, and memory separate. They can be together. Sure, why not? If that's the case, even better. And that's what should be done, in my opinion. So now, based on that, now what can we do? I mentioned that we have to make it non-volatile. It's a volatile, power off, your information disappear. You really want to power off, you remember. And then you power up again, it's what you had before. And of course, you all know this is non-volatile, right? Stay, right? If we can do that, then what happened? Your dynamic power system, ultimate limit is the KT ln2. ln2 meaning it's a 50% probability of on and off. And KT is the room temperature. This is from Landauers and Shannon and others. And being a given transistor, you have about, 10,000 electrons. Or N is 10,000. Times that is about, in the order of about femtojoule, roughly speaking. All transistors should switch. N is important. Now, what happens if I use a collective phenomena? Well, it turns out, first of all, in the magnetism, I remember, so I can get rid of this power on problem. The other one is collectively, they flip down and up as one logic unit operation from information point of view. N is nothing but 1. So now you save N times. And in fact, this work is by Anna's previous advisor, Professor Dada in Purdue, show that that's the case. So you have all this advantage of eliminating these two problems. In addition, this is a metal case. I don't have a semiconductor, so I don't have the substrate issue anymore. So I solve all the problems I mentioned, the two major problems. And so in passing, I should mention there are other issues, but in interest of time, I will not go further. So issue meaning other opportunities. So now, I mentioned this is important now. You have to remember what they are, so that's really going back to the memories. So memory is important for other reasons too. For example, over 70% of power consumption of smartphone is dissipated when you retrieve the memories. And in fact, all the Google servers and Microsoft, Amazon's server, 50% also dissipate. This is cited by ISSCC 2010. So memory is important. In fact, if you do well, then you can put it together with logics. That's what the system I'm driving to. So now, in the memory, we want to be as high density as possible, as fast as possible. That would be ideal case. And as low energy as possible. So I would have an energy scale from you to me here. That would be lowest energy, this scale. So the highest density, cheapest. And highest density and high energy is this hard disk, right? It's right here. The second go first is the flash, and your jump disk. Jump disk, which is about 100, is very slow, and energy also quite high. Density is pretty high. DRAM is what you use that for this computer all the time is red. Again, it's the is the volatile memories. Now, of course, SRAM is very fast, which is in the cache, right? But they are worst. Why? The density is so bad. You buy the expensive computer, you think you buy 8, 9 gig. It's not. You're paying 8 gig is this kind of memory that I showed you before. Not this. This only 12 to 16 meg only, very small amount. Because they're so big, they occupy already half of your CPU chip already. And that's your problem, right? So we think with the magnetic memory started from poor at the very beginning and make tremendous progress to spin transfer torque. This memory is like use Ampere's law. I call toggle memory, Ampere's law. And this one is a change by passing current directly through the devices and therefore use electron spin itself to change the magnetic property called spin transfer torque. And then I will talk about the magnetoelectric. In other words, I get rid of current, just use the voltage. There we believe we'll get lowest energy, higher speed, and high density at the same time to achieve this almost ideal embedded memories. Now, if we have embedded memory, we have almost like a brain function, or it becomes memory-intensive system. And that will become volatile electronics. So this route is actually beginning is nothing new. I'll tell you the aspect of it. From the toggle, which is Ampere's law, like a relay, for example, in early day, that in the control data system about since 1965 or so, you have 3-inch by 3-inch card. That's 4K memory. And these are truly non-volatile. You power off, power on, makes no difference. In fact, if you were as old as I am, in 1960 computer, you can shut it down, turn it on, it makes no difference. It stays the same state. And that's because of this memory. It has 2 wires with a coil and change current direction, Ampere's law, to change magnetic property. Now, what we really want to do is make it into a small scale, and that is called the spin transfer memories. And normally it has a hard magnetic layer down below and a very thin tunneling barrier and a thin flexible magnetic layers. That people refer that possible silver bullets. In other words, you meet all the low cost, high density, high speed, and non-volatile criteria. That seems to be the interest of it today. So I would like to, by the way, in passing, I should mention the so-called spin current is this ratio of ratio of the spin polarization factor P is a ratio of spin current over the total electron current. That's what that is. Now, a simple physics describes what spin transfer torque STT memories are. It's a very thin layer, so it can go up or down. This is a thicker layer, so it stays put one direction only. And this is one thin 1 nanometer insulator. And this structure is called magnetic tunnel junction, MTJ. So you now pass current in this direction, meaning electron in that direction. When you see this magnetic, they get all polarized in one direction because it's a very hard magnet, right? And they will tunnel through. This is very thin, even though I draw thick here for illustration purposes. And then you go through and see this different direction, it will torque over, change the direction. That means from anti-parallel to parallel. If now I want to reverse this process, how do I do that? Go back to this figure here. Pass electron through here. Now this is soft layer. Soft layer means it's not 100% polarized. So some up, some down. And that's some up, some down, a tunnel through. Now, for those same direction will go through, go by easily. For those different direction, as you see the hard wall, like I threw the ball to the hard wall, what do? They refract. So that's refract back, you see the direction again, opposite, you torque this one back. And that's how you change from parallel to anti-parallel. The difference of resistance gives rise to memory. That's it, and stay put. That's the change called from the Ampere's law to spin transfer torque. And this, of course, conceived in 1996 by Stromzuski and Berger, and shows very important, and the first time be able to take the energy down and dropping the current way down. And that's the spin definition. So a detail more physics-oriented is looking for the is governed by so-called Landau-Dirichlet-Gilbert, and that is nothing but Newton's law in angular momentum. So magnetic dt is change of angular momentum, right? And change of angular momentum, just like you play in freshman in gyroscope, and it has a gyration term, as if this is the effective magnetic field as if the gravitational force. So now you force this one to gyrate like this, right? Gyration precision like that. So this term is precession. And the second term is like a friction, is damping. So the damping term is right back, just like you gyroscope falling down, the same thing. Now, so this is the damping term. The next term is called, what Dzyudzhinsky introduced, is STT term. That is the anti because you push electron through here, you pull angular momentum into this direction or torque into that direction. So be able to switch from this direction to that direction. And that is spin transfer torque in physics, really. And it's really like Newton's law, except in vector form because angular momentum. And of course, that you compare to that one, always people refer this m cross p in this direction is if there's an effective field, and this effective field in this in direction, so that you can torque this one back here. That's a very simple description of spin transfer torque. And in fact, I repeat again, you go direction, this damping, the spin torque, and the structure are shown over here. And normally, you have a different, if you have a in-plane magnetic moments, since 360-degree freedom, one has to confine one direction, so you need an oval shape to do it, or rectangular. Of course, that's not ideal. Ideal in terms of density, you want to be circular. Well, circular, you have 360 degrees, you do not know what direction to put it. The only way to do that is put a magnetic moment in a perpendicular direction, and that is known as perpendicular anisotropy, and that will give you highest density. So the whole society today is working on perpendicular magnetic memories, not an implant anymore, and that's what really that is, okay? So, and I show you that you have free layer, you have fixed layer, and you have MGO. That's a very simple description. In reality, there's a way to anchor this layer to be fixed like this direction or that direction, and that is called synthetic antiferromagnetic. With antiferromagnetic, it's like a pin. You pin this in that direction or in that direction any way you wish. And for today, everybody want to pin in the perpendicular direction. That's what you have. And you can control this. So you can do it in plane or perpendicular any way you wish. And in fact, you can show this indeed is perpendicular or in plane by tracing magnetic field moments. For example, if I apply magnetic field this direction and I measure magnetic moments, I see a thin layer becomes this, a very sharp transition, meaning that magnetic moment is perpendicular. If moment is in this direction, then you have a swoopy type of structure. So you can see that I can control the thickness of a thin layer is perpendicular, make it thicker, becomes in plane. And that's what today's knowledge. And you look at that, and you can measure resistance, and this resistance gives you memory, basically. That's typical memory structure. So, that, what's so good about this? Well, it turns out this is the first time people reduce energy beyond what 1960 was. And then be able to, maybe together with CMOS. Now, good thing about in CMOS industry, you do processing in silicon technology here. The processing temperature is very high, almost 1,000 degrees. Now, with the metal, you can deposit at below 450 degrees C. And that's called back end, all the metallization. So this can be deposited over here, and you can do a multi-layer. So the density can be tremendous. And that's the good thing about it. So from the back end process, and then you may not need the SRAM anymore, if it's because they're very fast. Then you can save all this space and save energy at the same time. So this is what we're thinking of leading to so-called non-volatile electronic system. Of course, you may think, well, this is current-driven. My talk is drive into voltage-driven. So I mentioned that already in 1965, you have this Ampere's law. And people believe cannot be scaled. Well, of course, another school continued, just like anything else. People die hard. I will think of something. I know you said it cannot be done, but I think of something. Well, think of magnetic bubble. Intel, IBM, 1970s spent millions of dollars developing this. Turns out, again, based on Ampere's law, still energy too high, so never going anywhere. They're replaced by the DRAM, which is volatile, but people live with it by waiting for booting, for example. Now, the STT-RAM come into play, the major change. You don't use Ampere's law. You use a Coulomb electron to torque the spin directly, and now it's on market, a 64 megabit on market already. And this is the same principle I'm describing again. You pass Coulomb through, you torque, and just like I showed before, and reverse. But I want to point it out, it does not have to be implant. Can be most of people now working on perpendicular, and that's what I show over here. The magnetic moment in perpendicular, and similar principle applies. Now, so what does it do to you? Well, it turns out in terms of energy, your flash memory is 1 nanojoule, and then PC RAM, and I'm working on it, is about 100 picojoule. FE-RAM is about 1 picojoule here, and resistive RAM is similar. The STT-RAM can be down another factor of 10 lower. So that turns out maybe ideal, but I'll tell you it's not quite correct. And the speed is very fast. So it's comparable to SRAM, which I mentioned, or DRAM, so you can replace them. That would be nice. Most of the important thing is this endurance. Flash memory that you have, how many times you can write before it fails? Turns out 1,000 times. None of you has ever written more than 1,000 times on your stick before you lose them. So that's the reason you don't know. You don't know because of that. Now, in order to put in the computer chip onto CPU, you need a 10 to the 15. And that's important to know that. So if you don't, then your reliability is a problem. Density is quite good. But OK, so this is what we have. So now, why I bring this one up? The STT seems very good, but look, the energy is still 100 femtojoule. DARPA gave us funding about 5 years ago. Asked us to develop with this spec. They gave you, they give you a lot of money. They give you $14 million in 4 years, but you have to meet the spec. They give you a spec, and we did it. They gave to 2 teams. One is our team. The other one is Grandis, is a company team, and they also made it. But then after they made it, they were acquired by Samsung for $100 million. So we made it, but we didn't get any. So, 100, we get this number, and the speed is very good. Stability 60 energy, meaning E is 60 over KT, 60 times KT. That translates more than 10 years. And that's what we did. But we get nothing in return, but that's OK. We are there to educate. But that energy is actually, you think it's small, but it's very large. Compared to 65 nanometer CMOS, every switching is only 1 femtojoule, still 100 times larger than the CMOS switching. So you cannot put 1 to CMOS so that make it all entire circuit non-volatile. So we think we have to make a transition from current-driven to voltage-driven. This is the current-driven I showed you before. You pass current through autonomic current and do a switching. Now, what happens if you make it thicker? So it's almost like a capacitor. 2 metal, 1 insulator in between. Now, your Gauss law will tell you, when applied the voltage, nothing should ever happen in the metal, because in metal, electric field is 0 by Gauss law, right, in metal. So nothing should happen. But yet, something happened. And that's the recent discovery in about 4 or 5 years ago, meaning that if there's an electric field, apply the voltage, there's no current. What happens then, in the very thin layer in metal, known as Thomas Fermi layer, magnetic has a d orbital. D orbital is about 5 times 2, 10 times the orbital. They have different symmetry. They could rotate this way, could rotate it that way in simplicity. Now, because electron rotate that way will produce effective field in this direction, right? If you rotate this way, effective in that direction. By changing the population of this occupancy, one can, in principle, change magnetic field in this direction and create that direction. So in other words, from perpendicular magnetic field to that direction. And that's called control and anisotropy. And this is actually a recent discovery only 4 or 5 years ago. Never before that you can electric field you can use electric current, but not electric field to control magnetic moments. And that's what has happened. And of course, people argue may not be due to this occupancy issue, maybe due to asymmetry of the so-called Rashba effect, but it doesn't matter. Its origins come from spin-orbit interaction. That's the important part of it. So now, how do you, if you, in the interest of time, let me ignore this for a second. The right into here. So if I measure how big this magnetic field change by electric field as function of E field, I take this slope. That slope gives rise to so-called the magnetoelectric coefficient. And that energy is divided by area and then divided by E field, give rise to about 37 femtojoule per voltmeter of the current of this material cobalt-boron ion system. Now, obviously, the objective is to increase this number as high as possible. If I increase the high, my voltage can drop. I can drop to 0.2 if I increase 10 times. So that's the idea. So in principle, you don't have the limits as in the case of semiconductor. You can continue to drop down to a few kT if needed. So that's the beauty of that. That will circumvent this is so-called substructural problem MOS, and that's the whole purpose. So 37. Now, 37 today is in practice. There's theory, some theoretical work we are doing from DFT calculation with my friends in collaboration. Seems 600 is possible. Well, 600 meaning 20 times increase in reduced in voltage. That's remarkable. So anyway, so if this is possible, I can switch this way, and then you can calculate the energy. It's below 1 femtojoule. Remember, CMOS is 1 femtojoule. Now I am same energy or even below the CMOS now. Then I can still put on top. Then I can put directly into CMOS, make the whole thing non-volatile. So I can power off all the time. What's the difference of the operation of what I show, STT, and this one? From the fundamental physics point of view, there's no major difference except this STT, I told you before, the spin transfer torque with spin coming over a current going through. Now, if I change that to voltage, then this is the STT. The voltage difference is that you actually produce effective field here, not pulling down. That's the only difference. So the description of that is change this term to that term. The rest of them remain the same. So from the algebra point of view. So what happened then is effectively it becomes a gyration, a precision around this axis. Now, if I time properly, I can stop here, so it will switch over. You can stop the other way, it switch backward. So I can use the time to swap to control the direction, and therefore I don't need a magnetic field, etc. This is just simulation of that. And indeed, that's how it operates. And we have built some prototype already, and I'll just show you initial state, and then of course, gyration stop right here, then you switch down to below. That's how you do it. So the difference between STT and the MeRAM, I call the MeRAM, is to use voltage control versus current. And you time it properly with precision, and precision actually much faster than the normal switching, which I call thermally activated, about a factor of 10 times faster. So that's good. So that's how it happens. So let me I know I have a time issue here. So you can time this and apply different voltage, control the direction of switching, etc. That's being worked out, and they're all given the reference also. Some part is being prepared as well. So, and you can separate between parallel to anti-parallel, anti-parallel to parallel with either in-plane or perpendicular, depends upon design you have, and you can switch all this. So right now, I demonstrate we already have 20 times reduction of energy, and we can go, in my opinion, 100 times or even 1,000 times better when we have a better material combination. And everything depends on interface. Remember, this very thin layer control the occupancy or the effect of spin-orbital interaction. So if one can improve this interface, then of course we can improve this ME coefficient by a factor of 10. Everything improved by a factor of 10, again, in energy. So that's the important part of it. Okay. So even as what we have, we benchmark, see how fast or how low energy is compared to STT, spin transfer torque, of different current density operation reported today, including ours. We see that as we drop down, we improved it by more than a factor of 100. If we have better material, better interface, this line goes further down. That's what, but this is what we got today. So you see, continue to scale while the current-driven device cannot scale. And this is analogy to 1980, when the industry switched from bipolar transistor. You all remember bipolar transistor, which is current-driven, and was abandoned because you could not scale accordingly. And that's the reason CMOS took over, because they scale so well since 1980 or so. So that's exactly the reason. So you can estimate energy. Actually, you can go to 100 autojoule by simple CV square times energy the estimate. So that's why we estimate this CV square times divided by 2. And in fact, the better material, this number going further down. And it's just based on the material we got today. So that's published also in IEEE as well as ISCCC in the past. Now, what does it affect into the density? Well, it turns out if you don't have current, your transistor size can be reduced. Transistor width is function of how much current you deliver. So if one reduces the current, then of course the transistor width reduced. And that's, you get all this advantage by between 3 to 12 times in that aspect. So I'm giving you the story how this could be. Now, yet I tell you then this map again. This is STT, the rest of them same as before. These two are the volatile SRAM and DRAM. And the reason we use these two is because endurance. That's the reason we use them. Now, I told you only this two has a very high endurance comparable to this two. They're only magnetic because you move electrons. You don't move atoms. Nothing moves atoms. So it's still very high. And of course, your energy is much lower. So we believe this one will outperform a competitive thing. So the voltage control, I show you from toggle to direct current to magnetic, to the magnetoelectric effect. So that's the important part. And density, we believe, can go very high. And that's what we're hoping for. So it's not there yet. In other words, the industry has not complete all this yet. This is still in the development stage. That's why I'm showing you. Although this is already in the manufacturing of the smaller scale. So one thing I'd like to point out, so we talk about scaling, right? If you look at the fundamentally speaking, the size of the devices based on the interaction. So spin diffusion in the order of about micron to submicron. The paramagnetic and domain wall in the order of about 10 nanometers. And of course, molecular down below is smaller. Now, what I would like to share with I told you with the toggle, they are not very good because they are high energy dissipation. And the spin transfer torque in the order of picojoule. And I mentioned that magnetic could down to somewhere here. Now, this effect I should mention, that's what I want to bring your attention, the spin Hall effect. So spin Hall, and this part I will mention a little bit later. Spin Hall, based on the fundamental different reason than regular Hall. In regular Hall, you apply magnetic field. So electron, by Lorentz force, you go this way. The valence band, the Hall will go to your left-hand side, for example. And then, of course, you have Hall voltage. In a spin Hall, because you have electron coming this way, for example, and see your nuclear force, for example, electric field that direction, this direction. But relativistically, they tell you there's a magnetic field in this direction. So you spin up, goes that way, and spin down is the opposite direction going down way, right? Classically, you can think about if electron moves that direction and bend this way, you produce orbital, produce the magnetic moments here. So cause it spin up to go that way, and the other direction the other way, same thing. So physics it can explain both relativistically or classically. So now you have electron spin up this way, electron down this way. You measure Hall voltage, 0, no Hall voltage. But people quote, there's a spin voltage, which is not really voltage, but the difference of spin, and that's called spin Hall. And Arshwan in gallium arsenide spin orbital interaction is very small. He has been able to measure magnetic moment by so-called curl rotation and measure this, a very small, 0.001%, very small. But he's so skillful that he used this enhancement, show beautiful color. And that's how you can publish in Nature. You need a color picture to be Nature, okay? So this is what I explained to you before. Now, a key parameter, so electron goes here, gets the called spin Hall angle. That is, how many get spin can be able to use for talking. It turns out that electron gets scattered, so lose some. So in early day, always below 0.1. Recent work by Cornell group, Daniel Ruff's group, show that they actually with a heavy tantalum film, which has very high electron spin orbit interactions. They show that they can get 12% can use that. That's a very high number already. And that's give a light of the use of heavy metal of spin Hall effect into this game. So now, at the time we thought, what's the ultimate of spin orbit interaction? Remember, when spin orbital interaction is so high, the semiconductor becomes topological insulator. So we've been working on the topological insulator. Before I say that, I should mention, how can I use that spin Hall for switching? For example, in regular spin transfer torque, I mentioned already, you go here and then torque this one, as I showed before. In spin Hall effect, as Daniel Ruff mentioned, says, for example, I pass current through here. Electron moves that way, and of course, you have a spin Hall, so spin up goes up, spin down goes down, and therefore torque this guy. So you flip this one. If you pass current opposite direction, or pass electron different direction, then of course, this go backward, and then spin down goes up, spin out, up goes down, and spin down goes up, and of course reverse the possibility of the flipping. So you can do both directions to switch. And this is much better, more efficient. Writing energy is better because you can pass current through here, not through the MTJ. Anybody knows if you pass tunneling current, it's always extra resistance, extra voltage. IV gives rise to power dissipation. So you don't want a high V. And hence, with this, it's much better. So that's the reason energy goes down lower. It's a faster switching, no current going through, so reliability improves. Hence, a tremendous excitement in the spin Hall last a year or so by using heavy metal. And I mentioned, but extreme case is a topological insulator. Turns out our group worked on topological insulator, and there's a history behind that. I will not go into detail. And we chrome doped the bismuth selenide, antimony telluride. The reason of doing that is to make a resistance better, etc. So that's a minor detail. And we can measure resistance, magnetic resistance, to see if the torque gets changed. And people use that. And I show you this beautiful material that you can grow on top of gallium arsenide, and the beautiful TEM by Professor Wang of Zhejiang University. See that this layer you can see that's known as a van der Waals gap. In other words, layer to layer, the van der Waals force, it has a gap and shows very nicely. And it's about, I think, 6 quintuple layer. Each 1, 2, 3. Each one is 5 stack of atoms. That's called quintuple layer. So there's about 6 quintuple layer. On top is a 3 quintuple layer. And now the question is pass current through using magnetic resistance. Then one can see effect. And let me don't go into detail except showing that this effect we discover is 5,000 times larger than heavy metal. Why so? Why so? I have a video to illustrate the fundamental principle. Here, So if this is heavy metal case, electron come in, and you torque this guy, and of course, electron gets scattered, so spin change direction, right? And then after change direction, there's no effect on this guy anymore. That's the case of that. Now, in the case of let me do one more time, just make sure that we're doing the right thing. Okay. See that? It gets scattered. Of course, that's not, I have not done the really good emulation yet, but you see the picture, it had no effect on this guy because the spin already changed direction. Now, if we change that to topological insulator, I remember topological insulator has special character. If an electron moves that direction, the spin always duck in certain direction. If I go backward, the spin also duck in the opposite direction, automatic lock. That's the spirit of spin of topological insulator. That's the reason people are so excited about this topological insulator. And see that? You come in here, and after scatter, it comes back to its original structure again because it sort of regenerates into the right direction to be able to apply to the next one. And that I call the regenerative spin polarization. That gives rise to the spin Hall angle, spin column divided by electron column, much larger than 1. Could be much larger than 1. So in reality, we have shown experimentally that compared to ignoring this detail, just showing this picture, that any change of this spin torque versus column density, the slope of that indicates you how effective you are. And this is our paper just coming out from Nature Materials compared to last year paper of tantalum, which is heavy metal, as I mentioned before. That's a comparison. And this comparison already times 1,000 times. If I did not multiply 1,000 times, that would be a straight line here you couldn't see. So the difference is at least 5,000 times. So the new discovery of regenerative spin polarization from spin is a very important one. So let me just skip this in the interest of time. And I wanted to just share with you about what it would be. Well, okay, how fast can I do? Well, I can do 0.1 nanosecond. That's what I have. But if I look at the temporal scale from the ferromagnetic, is in the order of gigahertz. But the so-called anti-ferromagnetic, that is, in the material, you have polarization and the other atom polarization that way. They cancel each other. That's called anti-ferromagnetic. It's analog to the optical phonon versus acoustic phonon, if we wish, in that scenario. So if one uses anti-ferromagnetic, actually speed increase 100 times. So I have asked to be able to estimate the energy, this energy scale versus time. With earlier days, you have this very high energy SRAM and DRAM, and STT take it down to here. With a spin Hall, it's possible it can go down depending on what material you use. I think with TI, you can go further down here. Now with the MeRAM, with the voltage control, I get down to about this region. But the speed remains about 100,000s of picosecond, fraction of nanoseconds or so. Now, with the faster switching dynamics of anti-ferromagnetic, one can, in principle, improve 1,000 times. That's the future direction that we are working on. So now, what did all this come up to? Well, it turns out now I have a lot of memory now, in principle, and those memory are non-volatile. In other words, take a power off, I still have memory. That's what happened. So in principle, that semiconductor industry will continue to work on this direction, in my opinion. What will be the fundamental change in implication to the information processing? Today's computer is so-called von Neumann computer, which the largest ever built by US, by this country, and everybody's competing. It's called Titan computer. It benchmarked at 27 petaflops, 10 to the 15 floating point operation per second. It used 10 megawatts roughly, occupy 4,000 square feet, and cost about $100 million. Now, our neuron, our brain is 15 watts and about 1 liter size, okay? Now, it has actually 10 to the 11 neuron cell in it. That's what you have. In order to simulate brain, people estimate you need 1,000 of this computer to do it. 1,000 of them. So neuron is important. I believe there's an implication to a neuromorphic system based on what I was talking about. So a few words about neurons. So we have gone through from Neumann system and from the relay to tubes to BJT, bipolar, to CMOS, and continue on. We believe Spintronics will come into play here. Then the look at the brain function. It turns out today's processor is roughly right here with your PC, and your human brain's roughly 10 to the 16. How do you get 10 to the 16? It came from, you have 10 to the 11 neuron times 10 hertz times 10 to the 4 synapse, right? So that's right here. Now, I think neuromorphic seems to be very good. How do we learn from that? That's the important aspect of it. So I believe Spintronics can be a possibility, and the energy can be even lower with STT and beyond MeRAM and the spin Hall effect, etc. You all know neuron already, so basically dendrites is like an input, and then you make a logic function is right here, and this is all the input. And then they have the axion to the potential propagation. This is like interconnect, and this one to the synapses. So it synapse to many memories. So think carefully. One logic operation to here, 10,000 memories. So it's a memory-intensive system. So if you want to construct that, you need a 400 transistor. And I believe with Spintronics, we can get much smaller. So now, how can we, nutshell, how does it put into the architecture manner? So that draw to my conclusion here. That is, I already show you the magnetic stuff. I think we can integrate with the CMOS, I believe, will really make our system non-volatile and therefore save tremendous amount of energy, improve the speed. That's what I have. And for embedded application in particular, and I told you MeRAM and the spin orbit torque by the topological insulator could be also. Now, getting back to the fundamental of information processing we have here, could it imply a major change? The first change before truly the neuromorphic system happened is that, look, I have this red stuff, which is power hunger, and I power off, and a tremendous bus latency here, so-called latency here. If I can replace them by Spintronics, will be non-volatile. It can shut down if I don't use them, so save enormous amount of power for Microsoft servers, for example. That's the first step. Then I can increase memory directly on CPU at density. I talked to Cisco. Cisco wanted 5 gig. Remember today, 16 meg SRAM. They want to be 5 gig minimum onto CPU directly. If you do that, you don't need this DRAM anymore, right? And everything non-volatile, I can power off anytime and speed up anything you want. But then, first next step, if I can do 8 gig, 12 gig, then I have memory intensive, sparse logic. I don't need many logic anymore. Everything is based on memory. And this memory sparse logic is exactly the brain function. The brain is sparse logics, because remember, the logic is only majority gate, only one exon 9. The rest of them are the find out to the memories. And that, I believe, to the first step to a neuromorphic system as a first step. There are many other approaches that we are working on it, but I will not go into detail. But that will create a name, so-called Neurotronics, will be the future for electrical engineering. I hope that's what we're looking for. So in short, I'd like to want to thank many of my students in FINA and WIN and FAME, and also in the magnetic. We're working on Petram, working on a lot of stuff here, Magnetoelectric, and others. And TI material, topological insulator, we have people growing material, study very hard. And I thank you for every supporting agencies here. And then, of course, many centers support as well. And above all, I thank you very much for all of your attention. Right, thank you. Bye-bye.
take a couple of quick questions.
Earlier in your presentation, you mentioned that the clock speed was limited by the amount of voltage you needed to apply your transistors. How much will the magnetic memory affect the theoretical ceiling on clock speeds for future processors?
So the question referred to the speed of today's CMOS technology because of energy dissipation. The question is, if I use the Spintronics and reduce energy, how fast can I go further? Now, in terms of Spintronics, the magnetic is limited with the ferromagnetic is limited by so-called the ferromagnetic resonance frequency in the order of 0.1 picosecond. So that's roughly about 10 to the, maybe close to 50 to 100 gig you can do in terms of speed. Now, to go further, then there's a Magnetoelectric approach that you can go to in so-called close to terahertz region, but that's far in the future. And of course, the question is then, when you take that approach, will energy increase? And that's subject to further investigation, but a beautiful question.
Another quick question?
Yes?
I'm wondering how the magnetic fields affect other circuitry underneath the memory cells, or are the magnetic fields just localized enough?
That's an excellent question. So your question is referring to how close they could be without mutual interaction of the magnetic cells.
Like, RF electronics and EM radiation that
Right,
you need
right,
like cell phones.
right. That's a very good question. So, in terms of the EM wave interactions, so let's take EM wave out for a second. The interaction among the cell, it depends on the dipole interactions, and we estimate you can go down to about 5 to 10 nanometer without a major problem. In terms of electromagnetic waves interaction, that we have not looked into that. It's also because electromagnetic waves normally in the cellular form is about 5 gigahertz or so. Now, in principle, the good thing about electromagnetic waves, if you package correctly, the interference is very small. So that's all I can answer you at the moment now. We have not done experiments on that, but excellent question.
Okay, with that, let's thank Professor Wang.
Okay, thank you very much.